Welcome to this new unit, and the first section of this unit is titled Average Rate of Change. But before we get onto that, what I would like you to do is think back to what you've already done. What you've done is you've completed a unit on limits, which I said was our first big idea. And what did limits help us with? Well, helped us with a few things. Helped us describe function behavior. It gave us new definitions for familiar topics, things like asymptotes and the idea of continuity. And yeah, it also helped us practice our algebra skills and make sure that those were still in good shape moving forward. Where all this leads us is our second big idea, which is the derivative. And what the purpose of today's lesson is to bridge this gap and figure out how we go from where we started to where everything's headed, because this idea of derivative is going to be something that's going to carry on for quite some time, and it's going to be there through the remainder of this course and into any other further studies you may have into calculus. So let's start with this idea of average rate of change. So before we go on to average rate of change, recall what just a rate of change has generally meant to us throughout the years. The word that we usually associate with rate of change is slope. And where we've seen it the most is with lines, with linear functions. Talk about rise over run. We've even had a nice handy formula for it. y2 minus y1 over x2 minus x1. Or, using the Greek letter delta to describe change, a change in y over change in x. And we've always abbreviated that with a nice lowercase m. Well, what average rate of change is going to do is help us describe situations where maybe we don't have a straight line, we have more of a curve. Say this parabola that I've just drawn. The average rate of change will still let us describe the slope between any 2 points on this curve, but notice that since it's not a straight line, the curve will deviate from the slope between these 2 points. And so what we say is that on average, this dotted line that I've drawn in would describe the slope, would describe the rate of change of this particular function. So the idea of average rate of change is that a continuous function f of x on the interval a to b has an average rate of change of f of b minus f of a, y2 minus y1, over b minus a, x2 minus x1. And you can swap those. You can do f of a minus f of b over a minus b just the same way that you can read slope in two different directions. And what this is also referred to, this average rate of change, is the slope of a secant line, just like we showed up here. Recall that a secant line is a line that intersects at 2 points. So let's go to our first example. Find the average rate of change of f of x equals x cubed minus 2x on the interval 1/2 to 3/2. Notice the little calculator symbol here. Tells me that when I get to the end, if I'm stuck with any sort of messy arithmetic, messy calculation, it's okay to go ahead and use the calculator to finish up the problem. We don't want to get tripped up on basic math. So in this problem, we are looking on the interval 1/2 to 3/2. And what we want to describe is, from my starting point at 1/2 to my ending point at 3/2, how would I describe the overall change in my function? Well, I could see that it is definitely increasing, but I can also see it started by decreasing before moving up. What this idea of average rate of change is going to help me do is ignore everything that went on in between and just describe what's going on along this dotted line that I've drawn in, the overall change in the function. And so to do that, we're going to look at f of 3/2 minus f of 1/2, y2 minus y1, over x2 minus x1, b minus a. Writing this all out, this is the spot where the calculator comes into play. Please don't waste your time trying to calculate things like these when it's not entirely necessary. And there will be times throughout this course where it'd be a good idea to push yourself to work without a calculator. But in terms of notes and in terms of practice on your own, use a calculator just to make sure that you're 100% accurate. Equaling this all out, we would get 1.25, or as a fraction, 5 over 4, saying that as we move along this interval, this is our rate of change overall. We're increasing by 1.25 in our y values or we're looking at a slope of up 5 and 4 to the right. Now let's look at an example that's a little bit more practical. At 1 p.m., Mr. Crisp is in Leesburg. I am right here. He drives 40 miles and arrives in Washington, D.C. at 2:30 p.m. And there's my distance of 40 miles. What was his average speed in miles per hour? Well, the first thing that we need to do is we need to define what speed is. And speed's a concept that we're going to hit right now, but it's also going to continue to come up throughout the course. And all speed is a change in distance over a change in time. And so my change in distance, I drove 40 miles. And my time now, being careful because it did stress, we want hours, from 1 p.m. to 2:30 p.m., that is 1.5 hours. And dividing that, we're going to get 26.667 miles per hour, or we can approximate that to about 27 miles per hour. If you've ever driven or ridden in a car, you know that that's not realistic. I didn't drive 27 miles per hour the entire way. In cities, I'm probably moving slower. Highway, moving faster. If I hit any traffic, which I probably will, I'm going to move very slowly. But overall, every hour that I was driving, I moved about 27 miles per hour. And that's the idea of the average rate of change. It's not going to stay constant because this isn't linear, but on average, that's how many miles I move in 1 hour. Now, the question that we need to build to is the one that follows this up. How fast was I driving at 1:30 p.m.? This is an idea known as instantaneous speed or rate of change. I want to know my speed at one moment in time. Well, everything that we have is all talking about a change from one point to a next. This is only one point right here, one moment in time. The only way that I could probably figure this out is by looking at the speedometer at 1:30 p.m. There's no other way for me to describe my speed at that point until we learn what we're about to learn. Continuing with this idea of average rate of change, let's take a look at a slightly different example. Find the average rate of change for f of x equals x squared minus 4x plus 1 on the interval x to x plus h. Now I've taken numbers out of the interval and instead used x and x plus h. No different though. This is still the start value to my interval. And this right here in particular, this plus h, is just the interval width. This is the exact same as if I had said something like the interval from 1 to 3. Well, that h would have been an interval width of 2. No different. But here's what I'm actually looking at. X squared minus 4x plus 1, well, hopefully we can recognize that that's a parabola. And what I'm thinking about is imagining that secant line, but being able to start wherever I want to. So let's give ourselves an x-axis and say I can start at x. I can move to x plus h, any width of interval that I want, and get the slope of a secant line. If I actually substituted in values, I would get what I'd seen in the previous example. I would actually get a value for this average rate of change. Instead, by solving this problem, I'm going to get the slope of a secant line anywhere. So let's set that up. F of b minus f of a is going to be f of x plus h minus f of x all over x plus h minus x, b minus a. Now it's going to involve substituting an x plus h into my function, which isn't too bad. Just remember the idea of composite functions. It means replace your x with whatever's actually inside the parentheses, minus f of x, which is just my original function, all over x plus h minus x. Now what I'm going to do is I'm going to expand out that numerator. X squared plus 2xh plus h squared, distributing this negative 4 minus 4x minus 4h plus 1. And the other thing we want to remember to do is distribute this negative sign over here. So minus x squared plus 4x minus 1 all over x plus h minus x. Now we'll see is that some nice things are going to happen to this long, complicated looking expression. I've got an x squared and a minus x squared. Well, those are 0. A minus 4x and a plus 4x, also 0. And a plus 1 and a minus 1, also 0. In the denominator, I have an x minus x, which are also gone. And what I'll be left with, 2xh plus h squared minus 4h all over h. And I can actually factor out an h from the numerator. Canceling out with the one I already had in the denominator will leave me with this expression. one where if I know that starting x and I know the interval width that I want, I would have the slope of my secant line anywhere. So to generalize, the slope of the secant line, the average rate of change on some interval x to x plus h, unknown starting point, unknown interval width, the equation for the slope of a secant line is f of x plus h minus f of x all over h. And just recall the over h comes about because you really have x plus h minus x, but those two x's cancel each other out. Now, what was the point of all this? Well, the point is to go back and answer a question we had previously, which was, how do I describe an instantaneous rate of change? How to describe the rate of change at one point? Well, that's what this expression is going to open up for us. We're going to move from talking about a slope between 2 points to a slope at just 1 point using a tangent line instead of a secant line. Well, how can we take that expression that we have for the secant line and use it to describe the slope of a tangent line at any point x f of x? Let's keep going with our example using a parabola. And say I wanted the slope at this point. Well, the problem is I need 2 points to use my y2 minus y1 over x2 minus x1 to use my slope formula. F of b minus f of a over b minus a. So what we do is we make up that second point, and we instead draw in a secant line. So here I am at x, and I've moved myself away some x plus h. And in order to get that secant line, the one that I know I can evaluate, for us to be able to use that secant line to figure out the slope of this tangent line, what I'm going to do is I'm going to take this point and physically move it. I'm going to slide it along this curve until it gets so close to my original point, x f of x, that I can't tell the difference between the two. What I'm going to do is let h, that interval width, get very close to 0. That sounds like you're approaching 0. That is a limit. And how to find the slope of a tangent line is to take the slope of your secant line and let the interval width approach 0. The limit as h goes to 0 of f of x plus h minus f of x all over h is the slope of a tangent line, and what's going to become known to us as the derivative. Now this entire explanation right here, I'm going to go over that explanation one more time at the start of the next section when we actually get further in depth on this idea of derivative. So if you don't get it quite now, just make sure, mark off some questions to the left for you to bring up in class so we can hopefully clear up any misunderstandings that we may have. And now that we have completed this section, please make sure that you review and summarize your notes. And when you are ready, please move on to the next section. Thank you.